So there's an important method for producing morphisms between representations, which is called the averaging trick for reasons that we'll see. So let's start with two different representations of a group G, maybe in two different vector spaces V and W, and I'll also give myself some linear map from V to W. Then there's a procedure which produces a morphism between the representations. So it comes with a formula. I'm going to define a new function called t prime. It's the following. I'm going to take the sum over elements of the group of the composite psi sub g following t following phi sub g inverse. And I'll divide all of that by the order of the group. So I'm taking the original linear map T, which maybe is not a morphism of representations, and it's sort of, it's not conjugating because I'm using two different representations, but it looks like that formula. And I do that for every element of the group, and then I divide by the order of the group. That's why it's called averaging. Then T prime is actually a morphism between the representations. Okay, so the proof is just a straightforward calculation. I need to show that for all elements of the group G, that psi sub A T prime is T prime phi A. Or in other words, because phi A is actually an isomorphism, I can replace it with its inverse on the other side. I have to show that this gives me back T prime. Okay, so let's just do the calculation. Psi A T prime phi A inverse. So there's the formula for T prime. I'm going to use the linearity of both phi A and psi A minus to move them across and inside the summation. So I can move all that stuff inside the summation. So I get psi A and then psi G T phi G inverse phi A inverse. Oh, but hey, a representation is a homomorphism. So that's really psi sub AG. That's really phi sub, well, G inverse A inverse, but I could also write that as AG quantity inverse. And now I do a trick that one gets to do here. I'm going to rewrite the sum by re-indexing the sum. So I'm going to think about H as being AG. A is fixed, but G is varying. But as G runs over all elements of the group, so does AG. So if I replace AG with H, I write it like this. But this is really just a sum over all the elements H of the group. And hey, look at that formula. Except for the fact that I call it H instead of G, that's just the formula for T prime. That's what I wanted to show. So it's a morphism. Here's a good exercise to see if you understood what happened there. Show that if T, which was a linear map, actually started out as a morphism of representations, then the averaging trick just gives you T back. That's just a consequence of the formula. Let me make a remark here. This uses the fact that the order of the group is finite, obviously, because I'm dividing by the order. And it's also using the fact that the field is the complex numbers. Really, it's using the fact that it has characteristic 0. So, as we've seen, there are fields where when you add up 1 with itself, many times that's never equal to 0, for no matter how many times you add it up. And the reason I need that is because I need in particular the order of the group, which I can write as 1 plus 1 plus 1, etc. I need that to be invertible in my field. It has to be non-zero. If, say, P, a prime, divides the order of the group, and F is Z mod P, this averaging trick doesn't work. Representation theory over fields of positive characteristic, fields like ZP, is called modular representation theory. And it's more complicated and works differently than representation over, say, the complex numbers. Let's do a quick example. You can really use this. So let's take two different representations, matrix representations in 2 dimensions. Let's let the group be Z4. So I'm going to write phi sub brackets k, that's going to be a to the k, where a is the matrix 0, 1, minus 1, 0. And psi brackets k is going to be the matrix b to the k, where b is I, 0, 0, minus I. Okay. I'm going to let my linear operator be the identity matrix. So if I do this, then T prime is going to be the average. So I'm going to take 1 over 4 times, well, so I'll get identity, that's k equal to 0, b a inverse, that's k equals 1, b squared a to the minus squared, b cubed a to the minus cubed. So when I work this out, I'm going to get identity, and then 0, I 0, and then identity again, it turns out, and then another 0, I 0. So there's my matrix which describes a morphism. This gives a morphism from phi to psi. In fact, it's obviously an invertible matrix, so in fact, I've just shown that those are equivalent representations.